Hello everyone, our project is implementation of chatbot based on sequence-to-sequence model. My name is Lu Xingyu and my teammate is Wang Zijing. So what is a chatbot? At the most basic level, a chatbot is a computer program that simulates and processes human conversation, allowing humans to interact with digital devices as if they were communicating with a real person. Now, there are many different chatbots on the market. Retrieval chatbots are often used in more commercial areas. A growing number of brands are using chatbots to serve their customers. Generative robots can engage in casual conversation with humans that is more like real people. In this project, our goal is to achieve a generative chatbot. The dataset we use is Cornell Movie Dialogues Corpus. It is a rich dataset of movie character dialogue. The original form of the dataset is shown in this figure. For convenience, we created a nicely formatted data file in which each line contains a tab-separated query and response sentence pair. The core of our chatbot is a sequence-to-sequence model. The input and output are both variable length sequences, and the length of the two sequences are not necessarily the same. Such problems are generally solved by encoder-decoder framework. Encoder RNN encodes the variable length input sequence into a fixed length context vector. We can generally think that this vector contains the semantics of the input sentence. The decoder RNN generates the response sentence in a token-by-token fashion. The first hidden state is the last hidden state of the encoder. After that, the decoder will calculate the new hidden state and output the first word, and then the new hidden state and the first word will be used to calculate the second word until a spatial token indicating the end of the sentence is output at a certain time, or the length exceeds a threshold, the output is ended. And the heart of our encoder is a multiplayer GRU, which means gated recurrent unit. GRU and LSTM are both variants of RNN. They are proposed to solve the short-term memory problem and gradient disappearance problem of RNN. However, the common sequence-to-sequence model also has a problem. There's only one vector between encoder and decoder to transmit information. It is likely that we will have information loss. This is especially the case when dealing with long input sequences, greatly limiting the capability of our decoder. So we use the attention mechanism. The feature of the attention mechanism is that the encoder no longer encodes the whole input sequence into a fixed length vector, but into a vector sequence. The purpose is to focus limited attention on key information so as to save resources and quickly obtain the most effective information. In the course of training, we used a couple of clever tricks to add in convergence. The first one is using teacher forcing. This means that at some probability, we use the current target word as the decoder's next input rather than using the decoder's current guess. This avoids the possibility of being wrong one time and then wrong all the time. The second trick is gradient clipping. This technique is usually used to prevent the exploding gradients by limiting the parameters to a range that prevents the gradient from being too large or not a number.
We trained the model on Ubuntu 20.04 system, and we trained it 50,000 iterations with batch size equals to 64. We set to save the model in a tar package every 1,000 runs. The advantage of saving the model in this way is that we can choose to run the model for different iterations of training. After the model training is complete, we need to run some tests to determine whether it works well. We first test the model with 50,000 iterations of training. After running the model, we had some conversations with chatbot. We found that for some ordinary greetings, chatbot will give some strange answers that are only suitable for specific situations. We suspect that overfitting occurs due to too many training iterations and insufficient dataset. So we decided to select the model saved when the number of iterations is smaller. We run the model saved when training to 4,000 iterations and had some conversations with chatbot. We found that the chatbot can still complete daily conversations, even more logical than 50,000 iterations. However, the problem remains that chatbot answer is too single. So we collected a large number of dialogue data sets on the internet, expanded the corpus to twice the size of original data set and trained again. Obviously, chatbot becomes more interactive after expanding the data size. In addition to some simple greetings, it will express its views and even ask us questions. To some extent, this performance has been very close to the dialogue between humans. In our projects, we use PyTorch with sequence-to-sequence model at the core to implement a single generative chatbot after expanding the dataset and turning some training parameters. Our chatbot is able to achieve basic small chat conversation. In future work, we can try other models such as transformer and so on to explore better training results. We also came up with an idea during the experiment. If we process the WeChat chat records with a familiar person into a dataset and use it for training, can we generate a chat robot that can imitate the chat character of a specific person? Perhaps such chatbot can alleviate the trauma caused by the death of relatives in some area of psychotherapy. And thank you, everyone.